Hello there, I'm Mark Walker. I'm a lecturer in mechanical engineering at the University of Hull. Today I'm going to present a piece of work that was funded by the Environmental Biotechnology Network, EBNet, and the Carbon Recycling Network. Now those are both NIBBs, networks in industrial biotechnology, which were in turn funded through by BBSRC as part of UKRI. The piece of work was done as a collaboration between the University of Hull and University of Sheffield, and the title of the work is Modelling the Decarbonisation of Carbon-Intensive Industries Through the Integration of CO2 Biomethanation, Assessment of Carbon Savings and Production Costs. Now I should say that this presentation is not the complete work that we did as part of this project, and actually there's a much more detailed report, and we're going to put the link to the report in the notes below this video, as well as how you can cite this report if you need to. So this is just the contents of my presentation. So I'll introduce the topic and specifically CO2 biomethanation. Then I'll summarize the approach that we used in this project, and I'll show two sections of results, focusing on two of the industries that we looked at, and then I will summarize the findings of the broader project afterwards. So first of all, I just wanted to explain in this slide what is biomethanation or CO2 biomethanation as I refer to it. Well, it's methane or biomethane that is produced through a biological conversion of carbon dioxide and hydrogen. And here's the chemical reaction that's taking place in that conversion. Now, the first thing to note is that the term biomethane, which I'm going to use through this report, is not consistently applied and has some ambiguity in relevance to CO2 biomethanation. So my definition just for today of biomethane is methane that is produced through a biomethanation process, i.e. a biological process that has converted CO2 to methane using hydrogen. Now, the reason there's ambiguity is that really another definition of biomethane might be methane produced from a biogenic carbon source. So my definition is slightly different to that, although I do want to make an important distinction between biomethane that comes from a biogenic carbon source and biomethane which may have come from a fossil carbon source. Essentially in this project it's all about where that CO2 comes from. So I'm not trying to make a controversial point here, but I do use the term biomethane to describe all the methane that has been converted through this process. In the report, we make a distinction between biomethane from a biogenic source and biomethane from a carbon source. So that's just to clear up that little point. Biomethanation in this project is defined by this kind of process flow diagram that we've got here. So we're taking some flue gas or off gas from an industrial process, and we are putting that through some kind of cleanup process, which would predominantly involve concentrating the carbon dioxide content and removal of any other impurities. We're then taking that purified carbon dioxide and we're putting it into a biomethanation reactor. Now, if you read about biomethanation of CO2, you'll find that there's two main types. One is in situ and one is ex situ, and it's to do with whether you have a dedicated reactor to perform this reaction, or whether you do this reaction inside an existing anaerobic digestion system. Now, both are fine and both are still CO2 biomethanation. In this project, we don't really make a distinction between them. It doesn't matter really from the point of view of this analysis, whether it's in or ex situ biomethanation. So CO2 has gone into our biomethanation reactor. The other ingredient that we need is hydrogen, and in this project that's produced from electrolysis, which consumes water and produces as a byproduct oxygen. These are not further considered. These crossouts are kind of the symbol for cutoff. So in kind of life cycle speak, we would say they are cut off. They're not considered in this analysis. It is worth remembering that they are important to the overall process, especially if you're considering downstream use of that oxygen, which could have benefits in terms of its industrial application or just as a byproduct for sale. So we got three red lines here, which are the energy, or in this case electricity, use for the three main processing units that are part of our biomethanation system. We are going to consider that electricity is supplied from renewables, or RES as I abbreviate later. And that's really key to using the biomethanation process as a means to decarbonize. If you're going to use electricity from natural gas or something like that, this is not going to make any sense. So I've got some wind turbines here, but I've got any kind of renewable electricity supply is considered. So we have a little bit of off gas, which is the non-captured gas that came from our industrial flue gas. Predominantly, we're interested in its carbon dioxide content, since we're doing carbon footprinting. We then take the biomethane that's produced from our biomethanation reaction, and there may be a downstream polishing step before it is suitable for downstream use, which may be in the industry that we're talking about. It might be used as a fuel, or it might go be exported through the natural gas network. Now, depending on your background at this point, you might be thinking, why would we convert hydrogen to methane? And so I did want to address that elephant in the room before going any further, because it may be that because hydrogen has such a higher value compared to methane, you may be thinking, well, that's just like burning money. So why would we want to do that? Well, the answer is somewhat contextual and nuanced, but there are reasons that we might want to produce methane rather than to produce hydrogen and use that as a fuel or export that and sell it. So my elephant's now been to some of my lectures and has graduated from the University of Mark Walker, and now understands that the answer is not as clear as perhaps initially thought, and maybe he's a bit more on the side of methane rather than hydrogen. And there are pros and cons essentially between the use of methane and the use of hydrogen, some of which are outlined in this table. So there are reasons we might want to use or to convert hydrogen to methane through this process. So on the plus side there, you've got, if you produce biomethane, you've got something which is generally much easier to store and easier to store safely. It's much easier to use because we have a huge range of appliances, existing appliances from domestic scale all the way up to very, very heavy industry, which is designed for natural gas use. And so its utility is potentially higher. We also have a mature market for methane, which allows us to easily sell it in very large quantities if we need to. We also have existing infrastructure for transportation. Of course, in the UK, we have quite an extensive natural gas grid. That's not the same all around the world, but in a lot of countries, there is a natural gas grid which allows us to export and sell huge quantities of biomethane if we have them. And that is existing infrastructure. Now, of course, there are downsides to using biomethane rather than direct use of hydrogen. You do lose some energy first of all, by running the different stages of the process to produce biomethane. So if you're just, for example, using electrolysis to produce hydrogen, you have to use then energy for carbon capture, you have to use energy for the biomethanation itself. But also, just looking at the energy content of the amount of hydrogen you need to produce biomethane, you lose some calorific value along that process. So there are additional kind of energy losses. There's additional costs as well. So here on the negative side is additional costs. Of course, we need a carbon source to produce biomethane in this way. And the last negative there is really to kind of capture that there's a huge amount of interest in hydrogen at the moment, and there is a somewhat lack of supply. But hydrogen at the moment has a very high value compared to its energy content, compared with more mature fuels, and that's partly because it's expensive to produce, but also there is a supply issue. There's a lot of hype surrounding hydrogen and the future hydrogen economy as well. There's also a perception that using hydrogen is a green energy source, or you might say lower carbon fuel. And of course, our elephant here knows that it's not that simple. It depends very much on how you produce that hydrogen. A lot of hydrogen that's produced today is actually produced from natural gas. And in that case, that hydrogen, although at the point of use, there is no greenhouse gas emission, definitely in its life cycle, there is. So it's not as simple to think hydrogen is a clean energy and biomethane is not. Of course, biomethane has methane in general has got some, understandably and correctly, bad press because it is quite a strong greenhouse gas. So if it is emitted or leaked or emitted directly, then this does represent a greenhouse gas emission, and so obviously that is something that needs to be considered as well. But I would say that methane from a biogenic carbon source, so biogenic biomethane, would in general have a lower life cycle carbon footprint compared with currently available hydrogen sources. So I think the point I'm trying to make here is that it's a little bit more complicated than just saying, "Wow, you're crazy if you want to convert hydrogen to methane." There is actually a kind of contextual argument that can be made for why we would want to do that and why that might be a good solution for part of our decarbonisation strategy moving forward. So moving on to the work itself now, thinking about the industries that were considered in this study. So we chose four fairly carbon intensive industries that are important in the UK economy. So we have on the top left cement production or clinker production. We have steel, so blast furnace production to produce steel. We have the ethanol industry, we were focusing on whiskey, so a whiskey distillery. And the last one was pulp and paper. And we considered an integrated mill. So these are examples of industries which produce significant emissions of greenhouse gases, and they're quite large industries, although they differ in their kind of relative scale. Cement clinker, so clinker production, and steel production both produce predominantly fossil carbon as part of their emissions, whereas the whiskey industry and pulp and paper mills produce a mixture of biogenic greenhouse gases, so biogenic carbon dioxide mainly, and also fossil emissions as well, so fossil carbon dioxide through their use of fossil fuel inputs for energy. So now I'll present a summary of the approach that was followed in this work. So in summary, for each of the industrial processes that we studied, so that was 4 in total for this work, we go through the following steps. We first of all define what is our baseline industrial process. So I'll come to an example of how that looks a little bit later. We then develop what we call a high-level design for how biomethanation is integrated into that industrial process. So we're looking at the integration here. We don't go into the nuts and bolts of how that integration is going to work. We stay at a kind of process flow level in order to develop that design. We then quantify important mass and energy fluxes, and we do that both for the baseline industrial process, so we're using mainly literature to do that, and then we use mass and energy balance calculations in order to then look at defining some of those mass and energy fluxes also for the hypothetical decarbonized version of the process. So then we gather relevant data from literature in order to perform our two main analyses that we're going to do as part of this work. So that's we analyze the greenhouse gas emissions, and we make a comparison between the baseline and the decarbonized process, and we do the same for the costs associated with the production of those 4 different products to give us a cost for our baseline and then a cost for our decarbonized product. We then importantly do a sensitivity analysis in order to understand the effect of what is quite a large amount of uncertainty about some of the kind of parameters that we use to build up all these models and do all these calculations, just to understand a little bit about how those uncertainties affect our results. So in order to do this piece of work, we had to define some principles of our integration. And these are set out here. It's kind of an ideology, really, to state that what we're trying to do is we're trying to achieve something we refer to as a drop-in retrofit. So there's an existing industrial process, and we want to build into it the retrofit of the biomethanation integration. And that's because a lot of these facilities, these industrial facilities that do in these 4 industries, are extremely long lasting. So when you build them, they might last 20, 30, 40 years before you want to rebuild them. And at that point, you might redesign everything and do something like electrify, for example, some of these industries, rather than doing this kind of design. Anyway, so this is the kind of set of principles that we followed. So in terms of, just to kind of briefly go through them, we make no distinction, as I said, between in or ex situ CO2 biomethanation. We only consider that there's a chemical conversion and how much of that CO2 is converted. So any gas, the second one there, any gas which contains CO2 that's produced by our industrial process is considered as a candidate for the biomethanation process. And if it wasn't pure, it would be sent to a carbon capture process. If it is relatively or completely pure CO2, then it could be sent straight to biomethanation. Third, any natural gas input to the baseline process after the integration would be, that natural gas input would be replaced with the produced biomethane as a like-for-like drop-in fuel. We also then considered that other fuels used in the industrial process could also be substituted with biomethane. It's not always possible to do that without redesigning the whole industrial process. So we've said where it only requires minimal process adjustment. Okay, so then if we have excess high-grade thermal energy as part of our ethers that was available from the existing baseline process, or through the kind of modifications that we made, we would say that would be able to satisfy the thermal demand for the carbon capture. So that's assuming that the carbon capture is using an amine scrubbing based technology, that the main requirement for that energy requirement for that process is a thermal energy for the reboiler. But where there isn't sufficient excess high-grade thermal energy in our industrial process, we would then use any excess electrical energy that was produced on the site itself. So several of our industrial processes commonly have on-site electricity generation. And so where that electricity is available, we would redirect that to satisfy the energy requirement of the electrolysis or the carbon capture. So in that case, we'd be using electricity from the industrial process to supply thermal energy, in this case, to the carbon capture process. And then any remaining net energy requirement from both the decarbonized industrial process, and that's split into the industrial process itself and the integrated biomethanation process, would be sourced from a kind of externally produced renewable energy, renewable electricity, and we've considered different types of renewable electricity in the analysis as well. So these principles allow us to move forward with the work and to make the designs for our decarbonized industrial processes, as well as to do the calculations needed for the mass and energy balances, the greenhouse gas emissions analysis, and eventually the costs. So now to define the approach for the carbon footprint calculations that we did. So for each industrial process, we would define a baseline industrial process, including the upstream and the downstream supply chains, and we would get information from literature about its carbon footprint, as well as define all the major mass and energy fluxes that were relevant to our analysis as part of that industrial process. I'm labeling on here the scope which could be assigned to these emissions as per the greenhouse gas protocol approach as well. These scopes refer to our entire system. So there's a caveat here that if you see me referring to scope 1, 2, or 3, these are with respect to our complete system and may not be the scopes that would be defined if you were the owner of this industrial facility. So there's a little bit of nuance there. So anyway, once we've defined our baseline carbon footprint, we then do our work based on the principles that we defined of designing the biomethanation integration. That has multiple different parts. So first of all, we have our biomethanation, which takes our CO2 containing gases. Our biomethanation box here on this flow diagram is everything that was in the original diagram that I showed about what is CO2 biomethanation. Okay, so it includes the carbon capture, it includes the electrolysis, and it includes the actual biomethanation reactor itself. So inside this box is 3 major systems, but a fair amount of engineering complexity, but we keep it simple at this high-level design. Into that goes renewable energy, and we produce biomethane. Now, some of that biomethane is going to go back, as I said, and be used in the industrial process to replace, I've used the word substitution on the diagram here. So it's going to replace predominantly natural gas, but also potentially other fuels in our industrial process. There's also going to be biomethane exported from our site. We're going to have quite a lot, in fact, in all our cases, we're going to have a lot of biomethane produced, a lot more than we can use, and we're going to export that. Okay, and somewhere downstream, that's going to be used. So we are including the downstream use of this biomethane in our analysis. I would also note that there's this box here, which is the modified energy input. So this is just to remind us that by integrating biomethane into our industrial process, we've changed the energy use of our baseline process. And so this here can represent a multitude of kind of mass fluxes of different fuels, but it's just there to remind us that there has been a change. Okay, so this is our system boundary for the decarbonized process. So note, just from a carbon footprint point of view, we are including in our system the renewable energy supply, and we are including in our system the downstream use of our biomethane. If you are the industrial process operator, you may well not think of those things as part of your system, which then is this issue about how you define the scope of the emissions. So then we've got a baseline carbon footprint, and we then basically look at the difference between what's in our baseline and what's in our decarbonized system in order to calculate the decarbonized carbon footprint. So it's just a series of addition and subtractions at this point, although to get there, there's quite a lot of calculation. So what the first one here that I just highlighted, so there's some emissions in the supply chain, or I should say in the life cycle of the renewable energy supply. So despite this being renewable electricity, there is still definitely a carbon footprint. It's a lot smaller than it is for fossil electricity, but it still exists. So an arrow coming out of our system represents additional emissions in this case. Okay, so then we avoid some emissions as well, because we have, instead of emitting all that flue gas or CO2 containing gas into the atmosphere, we've now captured it and we don't emit it. At least we don't emit it at this point in the process. So this is a negative on our, it reduces the overall carbon footprint of our decarbonized process. We then re-emit some of that because our carbon capture process isn't 100% effective. So some of that is re-emitted. So we have to account for that. Now, we then, because our downstream use of biomethane is included in our system boundary, we can do what in life cycle speak is called, we can do a system expansion or a substitution. Okay, so this biomethane, when it's used somewhere in our economy, actually leads to a reduction in the use of natural gas, because it's just used in place of natural gas. So that's why we call it a substitution. What that does is it can reduce the effective emissions from our system because we have avoided the use of a fossil fuel. So that's what this arrow represents. But we have emitted, by using that biomethane, we have emitted a certain amount of greenhouse gases. So these numbers, if this is fossil biomethane, so I talked before about we can have fossil or biogenic biomethane. If this is fossil biomethane, actually these two numbers end up being quite similar. Now, they're not exactly the same, because these two fuels are not exactly the same. But the other reason they're not exactly the same is there are supply chain emissions associated with the production and distribution of natural gas. So that adds a little bit as well. So it ends up that these two are similar, but not exactly the same. We also have changed the indirect emissions from our from our industrial process, because we've integrated biomethanation. So that could be a net positive or a net negative, depending on what we've done. So that's the method of how we calculate the carbon footprint. Now, there are exclusions from that. So we haven't included any of the indirect emissions which are associated with actually building, and eventually decommissioning this additional equipment associated with the biomethanation integration. So this is an important exclusion, important to note, but it's probably not going to be a huge contributor over the lifetime of this equipment. There's also the two things that I said were excluded. So water supply, again, it's not expected that this is going to make a very big difference to our carbon footprint. And eventually the same can be said for the oxygen production and its eventual use somewhere, either in the industrial process or outside of our system. So those are kind of exclusions, known exclusions from our analysis. And the approach for the economics part is fairly similar to the carbon footprint part of the project. We essentially take the production costs of our baseline product, be that steel, whiskey, paper, or clinker. So we get that value from literature, and then we look at what extra costs we've incurred, and we also look at what extra revenues we can generate from the integration of biomethane to come up with a decarbonized cost. So what that looks like, first of all, there's new costs associated with the building, operation and supply of energy so this is CapEx and OpEx for all our new kit that we've used for that integration. So there's a whole bunch of extra costs that we have to bear. And then we also have our new revenues, and we've also made some savings relative to our baseline production process. So we're now selling biomethane. We've also reduced our fuel use through our reintegration of biomethane into our industrial process. And it's essentially a sum. We make it look simple here, but there's a heck of a lot of calculation required to get to these final values that we can just add together, and refer you to the report for all the detail of how exactly we did that and all of the kind of how the mass balance and energy balances follow through to the eventual calculation of production costs. We are not considering any incentives, government incentives, carbon tax, nothing else, only the production costs themselves. So definitely you could extend this analysis to look at the analysis of perhaps government subsidies or government incentives to encourage decarbonisation of these industries, but we're not including those in this report at all. So our analysis, I mean, there's a few caveats here. Whenever I speak about this work, I do like to just say that it is a fairly simple analysis in some ways, and so it's definitely not a full bottom-up techno-economic analysis. And it makes some simplifying assumptions. So we can kind of say this is a broad stroke approach, really. So we have fixed unit costs for our costs, revenue and savings, which assume no scaling effect. So that's obviously a big assumption, especially considering that there's kind of several orders of magnitude in scale difference between the smallest of our kind of industrial facilities that we've analysed and the largest. So I think the way I put this in a suitably vague fashion is the results can be considered indicative and perhaps good for comparison, but we are not claiming any kind of accuracy in terms of the prediction of costs associated with this type of decarbonisation. So on to some results. So in this presentation, I'll only cover results from cement clinker and pulp and paper. The reason for that is not just to keep the presentation a little bit shorter. All the results can be found in the report, which can be found in the links below. The reason I'm doing clinker and paper mill is because whether the main carbon flux through our industrial process is fossil or biogenic makes quite a lot of difference to the analysis. So I'm showing one of each. Clinker will be our kind of example of a mainly fossil carbon industrial process, and then pulp and paper is an example of an industrial process where a large fraction of the carbon associated with it is biogenic. So this slide simply represents the outcome of our kind of analysis of mass and energy fluxes into a production facility for cement clinker. So this is then used as our baseline industrial process for all our calculations then into our decarbonized process analysis. So the first thing to present is just the kind of high-level design for the decarbonized industrial process. So what we've added onto the diagram on the previous slide is our integration of biomethanation. And so this flow diagram just shows the kind of fluxes of energy and material which are associated with that integration process. So everything here has been made specific to a ton of clinker, such that it then allows a kind of comparison of the different energy or mass fluxes that are associated with the decarbonized process. Again, everything is explained in more detail in the report, and if you're interested in how these numbers were calculated and where they came from, please refer you to that. So after performing our mass and energy flux calculations for both our decarbonized and baseline process, we can then go on to calculating our carbon footprint. And I've chosen to present these results as waterfall diagrams, and this allows us to see the different categories of reduction or increase in greenhouse gas emissions. These align broadly with the fluxes that I showed in the approach section when I was describing the approach to the carbon footprint. And so it may be that this graphic is best viewed alongside those schematic diagrams that show those different changes to emissions that occur as part of the integration process. So let's start with our baseline carbon footprint for our clinker. It's 870 kilograms of CO2 equivalent per ton of clinker, and that is obtained from literature. So what happens? Well, first of all, we avoid emitting a huge amount of that greenhouse gas because we are capturing that carbon as part of the biomethanation process. Our biomethanation process is not 100% effective, and so some of that actually is emitted. So we add that back on, and it's about 10% of that is not captured. We avoid the use of natural gas because we have instead replaced it with biomethanation in our decarbonized process. But we are using a lot of renewable electricity, which does have a life cycle carbon footprint. In these calculations, it's assumed to be wind energy in the UK. So our electrolysis, carbon capture, and biomethanation processes all use electricity, and that has associated with it a carbon footprint, which is small per unit of electricity, but we are using quite a lot of electricity to do this. So these values are all part of the calculation. So we're still moving now towards our final decarbonized carbon footprint. What's left? Just a few things. We have our transmission and distribution, so the emissions associated with our electricity grid. So we're using a lot of grid electricity, and there is emissions associated with the transmission and distribution grids. Now we account for the emissions associated with the downstream use of our biomethane. This is the biomethane that we've exported. So somewhere in our economy, this biomethane is going to be burned. It's fossil biomethane, and so it therefore emits fossil greenhouse gases when it's combusted or when it leaks. So this is accounted for in this quite large chunk of greenhouse gas emissions. And then we've got the other side of that coin, is that by producing this biomethane and putting it into the gas grid, we've then avoided the use of natural gas. And so that's this substitution that I was talking about. Or you could also say, by doing system expansion, we can account for these emissions that are reduced somewhere else other than our industrial facility. And as I said before, that is slightly larger than the emissions that we produce from our biomethane because of the supply chain, essentially. So it's not just the direct emissions, it's the direct and indirect emissions associated with natural gas. Okay, and then we've reached our answer. So with all the assumptions that we've made and with the system boundary that we've drawn, including this substitution that we're making between our, in this case, fossil biomethane exported and natural gas. So based on that system boundary, we can then say that our decarbonized clinker has now a much reduced carbon footprint of 166 kilograms per ton. So this is a significant decarbonisation. Obviously, it relies on the substitution for biomethane for natural gas with biomethane, and so there's a kind of built-in assumption to that our gas grid has not been greened. So we do take into account the biomethane that's already in our natural gas grid, but it is a very small fraction at the moment. And so one thing that will happen is if we start reducing the amount of natural gas compared with the amount of biomethane that's in our gas grid, the effectiveness of this kind of substitution in terms of a decarbonisation effect becomes less. So let's just say that this relies on our gas grid being predominantly fossil based to kind of allow this assumption of a like for like substitution to hold in our carbon footprint calculation. Now, I said we did some sensitivity analysis, and I'll just show that in a minute. But if you stack up all of the kind of main sources of uncertainty that we think are in this analysis, you can see one issue here that if we make a kind of best case estimate on everything, so everything is as efficient it can be, everything is as low carbon as it can be, everything works as well as we think it can, we get a very, very low carbon footprint for our clinker, even as low as 5. But on the other hand, if you make all the worst case assumptions that we've made in our calculation, you actually slightly increase the carbon footprint of your clinker. So it's just an important caveat of this work that there is inherently a lot of uncertainty associated with it. This is our kind of best guess of everything, so we're not. I definitely think that's a positive result, but it is just always worth remembering that their effect of that uncertainty is very large. And just to kind of break that down a little bit, these are what we think probably are the most influential sources of uncertainty, let's say, or error in our analysis. So what we've got here is a sensitivity analysis looking at various kind of parameters, important parameters that we could that we use in our calculations, that we could vary in kind of realistic ranges. So each of these quantities, so the amount, this is like the effectiveness of the carbon capture. We varied it between 80 to 100% in terms of the amount of carbon that is actually captured by that carbon capture process. How much energy carbon capture uses, how much energy electrolysis uses, how much energy biomethanation uses, the actual biomethanation reactor, how much, and I mentioned this before, how much biomethane is there in the gas grid. So currently, I believe the figure is somewhere, well, a lot less than 1%. But we've said, okay, what if it varies between 0 to 20%? And then probably, as you can see from our sensitivity analysis, the grid intensity, so the carbon intensity of our electricity supply, which we varied between the kind of best case estimate, which is for onshore wind. And in our worst case estimate here, we've used the carbon footprint of bioenergy effectively, which is the most carbon intensive of what we consider to be the kind of renewable electricity production processes. The nominal value, which is the value that produces the main result, was for the average carbon intensity of renewable electricity in the UK grid. So what do we take from this? Well, first of all, these uncertainties or kind of sources of error make a lot of difference to our result. So you can see the kind of result of our calculation down here. So where this axis, where the y-axis crosses the x here, is our main result. So you can see that's the result that we got from on the previous slide, and then obviously these bars represent what happens when we vary our assumption about these parameters. So yes, how effective is our carbon capture process clearly is going to affect the overall carbon footprint of our product, because it determines how much of that is just emitted on site by our carbon capture process. The energy consumption of carbon capture is relatively, the effect of the energy consumption is relatively small, and the same, even smaller for biomethanation. If we can make electrolyzers more efficient, then obviously we can make a reasonable chunk of difference to our eventual carbon footprint, and that's because we use a huge amount of energy to produce the hydrogen through electrolysis as part of our system. Yeah, by far the take home from this is, however, that the electricity that we choose to operate our system on, predominantly the electrolyzer, makes a huge difference to the calculation of carbon footprint, such that it can almost, on its own, just by using the kind of upper end of renewable electricity in terms of its carbon intensity, it can almost write off any carbon savings that we may make as part of this integration. So here's our equivalent diagram for clinker, but now looking at production costs. So I don't need to go through this waterfall diagram step by step, because now you've seen one of these, you understand that there's a baseline cost that we start with, and just like in the carbon footprint, we then look at what the positives and the negatives that contribute to our decarbonized cost over here. So the cost of carbon capture, the cost of hydrogen, the cost of biomethanation, and the cost of injection into the natural gas grid are all additional costs that we bear. And then we have revenue, in this case 73 pounds per ton of clinker in sales of biomethane. This F here means it is fossil biomethane. So this is not biogenic biomethane. So, and the important take home here is that this adds huge cost to our process. So this ain't cheap. And the main chunk of those costs is our generation of hydrogen through electrolysis. So I think it's commonly known that the production of hydrogen through electrolysis is expensive, and yes, you can see that comes out in our calculations as well. Again, we've done a kind of, if you stack up all our kind of major sources of uncertainty, you can get best case, worst case. Our best case 237 and worst case 842. But you can see that in any case, based on our kind of set of assumptions, there is a very large increase in costs associated with this integration process. And onto the second set of results that I'm going to present. So this is for paper production, which is one of the other out of the four industries that we are covering in this work. You can see that our baseline process flow diagram and energy and mass fluxes were taken predominantly from the source that you see there. And here you can see then the diagram showing the mass and energy fluxes for our decarbonized process after the integration of biomethanation into our industrial process. So it's a little bit more complex than the case for cement clinker, and that's because there are some additional opportunities for integration. So not only can we use biomethane as a substitute for natural gas, for example, in our lime kiln, but we also can take some heat from the recovery boiler, which is part of the integrated pulp and paper mill here, and we can use some of that heat, in this case in the form of steam, in order to operate our biomethanation process. There's also a power plant on site in this example, and I believe in a lot of pulp and paper mills as well, integrated mills, that they have a power plant on site, which would also be generating energy from steam from a recovery boiler, but also steam from a biomass boiler as well. So here we've got 3 sources of CO2 containing gas. You can see. Now, another interesting and kind of important point to make here is that after our integration with biomethanation, there's now no fossil carbon. There's no fossil greenhouse gas emission associated with this system anymore. Before the integration, there was natural gas being used in a lime kiln, and so despite this being a pulp and paper mill with a large flux of biogenic carbon passing through it, not all of the carbon prior to the integration was biogenic. However, now after the biomethanation integration, it is all biogenic carbon in the direct emissions from this. So obviously there's still fossil emissions in the life cycle of this system, especially in its construction, commissioning, decommissioning, end of life. But in terms of the carbon flux, it's all biogenic. As before, all of the numbers have been made specific to, well, we've used 2 kind of ways to represent our data here. You've got the overall scale of the pulp production. So that's AD in this case is air dried ton. So that's tons per day. So that gives you an idea of the scale of the operation. And so each of our fluxes of energy or mass has been corrected to a kind of daily amount. But also we have made everything for our calculations. What's most useful is to make everything specific to that 1 air dried ton of pulp that's produced. And so each of these, there's 2 figures which relate to both the overall daily and then the per ton amount of energy or mass in our decarbonized process calculations. So it's worth just having a little bit of a rewind here, so that there are some differences which in terms of the kind of organization of our carbon footprint calculations, which I'm just highlighting on this diagram here. So now I'm making a distinction between fossil emissions, which are in this case blue. So those relate directly to the diagram which I used to describe the approach to our carbon footprint earlier in this presentation. Just for clarity, there's a downstream supply chain here which is not included in our system boundary, and that's for the pulp and paper mill specifically, and that's just because our baseline carbon footprint doesn't include those things. So the system boundary for this system is a little bit different from the system boundary of the others. It doesn't make that much difference to our calculations. But what does make a difference is the effect of biogenic carbon. So green, I've now got green arrows which represent biogenic greenhouse gases. Okay, so let's just look what they are. So first of all, now we're still avoiding downstream use of natural gas, and that's fossil emissions avoided. But our downstream emissions or from our now biogenic biomethane are biogenic greenhouse gases. Okay, this is going to make a difference in our calculation. The reason it makes a difference is because these emissions here of biogenic greenhouse gas emissions are predominantly balanced by the upstream photosynthesis. So the source of the carbon in this biomethane is actually in the wood. So it's been taken from the atmosphere by photosynthesizing trees. Okay, so often in carbon footprint calculations. Direct biogenic emissions are ignored. Now, we haven't, and the reason for that is because they're offset by a kind of somewhere in the supply chain upstream, there is an offsetting every molecule of carbon that you emit that's biogenic, of carbon dioxide, sorry, has a upstream intake of carbon dioxide by a photosynthesizing plant. We don't ignore it here. We just put them both in our calculation. So this is it reduces our overall carbon footprint in our calculation. So that does make quite a big difference, as I'll show on the next slide. And this is the carbon footprint calculation. So this we already saw the waterfall diagram for the clinker earlier in the presentation. This is the equivalent one for the pulp and paper mill. And again, I've color-coded our biogenic emissions in green, and then the fossil emissions in blue. So there's a mixture of different emissions that in our system, produced by our decarbonized system now. So again, we've got a baseline here taken from literature, 950 kilograms of CO2 per air-dried ton of paper pulp. Now that photosynthesis that we have to account for in our system now is, and this is only for the carbon that's in the biomethane. This does not account, we're not trying to count the carbon that's ending up in our paper. That would be incorrect to try and use that. That's the carbon in that paper is already accounted for in our carbon footprint from the baseline process here. So this is additional carbon which ends up in biomethane at the end of the process. So this is quite a big negative, reducing our carbon footprint in our calculation. We then go through various other kind of fluxes of greenhouse gases. So we avoid direct emissions of fossil carbon because we haven't used natural gas in our process. So we avoid that because we've replaced fossil natural gas in our lime kiln with biogenic biomethane. So we avoid that. We still have a biogenic production of, we have a biogenic off gas here. That's because that's from our carbon capture process, remembering that all of our carbon flux that we have on our decarbonized process is now biogenic because we're not adding any fossil carbon into our system as a fuel. So there's a bit of avoided natural gas there as well. Right. Now we have the same categories as on the other waterfall diagram. So this is now equivalent to the clinker. So these are all energy carbon footprint quantities associated with our electricity use. Okay, so they are coming from our electricity grid, and there are fossil emissions in the life cycle of fossil fuel, of renewable energy. So here they are. We also, because we're, instead of exporting steam, so we're reducing the amount of steam that we are exporting, and so this actually has results in a net increase in the effective carbon footprint of our process because we're not exporting as much electricity as we would have in the original baseline process through that reintegration. And the same with electricity. So some of the electricity that we produce we're now using on our site. And so that results in a net increase in our effective carbon footprint. Okay, we're getting there. So now we are saying that there's instead of this being a blue column, we're now for our downstream biomethane. So this is biogenic biomethane being used downstream of our process after export into the natural gas grid, and that emits biogenic greenhouse gas. So this is a big positive. So you can see how these two now, why it's kind of a valid assumption to kind of offset these two quantities in a lot of carbon footprint calculations. Just say the net is zero, but it's not exactly 0, but it's pretty close. But we've accounted for the intake of CO2 in photosynthesis, but we've also accounted for our biogenic emission here. But this biogenic emission still substitutes for natural gas in our gas grid, which means we still claim the benefit of that substitution for fossil greenhouse gas emissions. So this is the avoided natural gas emissions downstream of our industrial process. Okay, so after all that, we can then say, well, now our decarbonized process actually comes out as a negative number. So we went from 950 positive, so that's the net emissions of our process, and now we are at a negative. And so that's not to say that our pulp and paper mill takes emissions net out of the atmosphere. That's not what this means. It just means that based on the calculation that we're doing, including the substitution for fossil natural gas, the net effect to the economy, you might say the economy's carbon footprint, is negative. It's a net reduction in overall carbon footprint. So they are a little bit different. It's not like saying it's not like carbon capture and storage, which truly does result in a removal if the carbon is biogenic from a net reduction in atmospheric CO2 if you then store that biogenic carbon. So on to costs for the paper production. So you can see a similar story to what we had for clinker. We have a baseline cost of our product from literature, and then we add on our additional costs. So there's 4 in this case, and then we subtract our revenue. And we have and they're all on the same basis. They're all per pounds per air dried ton, including capex and opex, and we end up with our final production costs. So there's still a large increase in production costs if you compare 395 with 2,609. One thing to note here that now the revenue that we're producing is assumed to be the same as a unit revenue as it was for the other processes, so then the fossil-based processes, and that's currently not realistic because the biomethane has a higher value than. So if you're selling biomethane, you can earn more than if you're selling fossil methane. But that's not accounted for in our analysis because we didn't want to distort the calculations. We want to give them in as kind of unadulterated way as possible. If someone did want to tweak our analysis to explore that, then that would be fine. And again, we've got best and worst case. So you can see even in the best case, there's still a significant increase in cost of paper production, and in the worst case, a huge increase in cost. So for both processes, we saw that the costs were increased significantly by the integration of biomethanation. Okay, so I've been through those 2 processes out of the total of 4 that we analysed as part of this project. The last part of this presentation is just to summarise some of the broader findings that we had. And the summary of our work is done with 4 main graphs. Again, these are shown in the report. But the first way to present these results was just to say, well, what's the decarbonisation effect per unit of product that's produced? So this is amount of avoided greenhouse gas emissions in tons of carbon dioxide equivalent per ton of product. And we get a range between 0.7 and 2.87 based on our results. So I don't think that tells you a great deal unless you just want to work out what's the potential saving of producing X thousand tons of clinker. Well, then this is the value you need if you're using that, if you need to calculate that. But they're not necessarily comparable because these are very different products. and produced in very different scales. So if you think about, a ton of cement clinker versus a ton of whiskey, they're quite different. So this is not necessarily the best way to compare our results. So the next thing we did, or one of the other things we thought about, was just to kind of show the relative cost increase. And actually, this is an important thing for to be part of this presentation, because for cement and paper and for paper production, the relative cost increases are very high. Now, actually, we didn't see such kind of large increases relatively for distillery and steel. Steel was still you would still call that large, 180% increase in cost. But for distillery, the relative costs were much more modest. Again, it's not a good way to compare our 4 different processes, because they are very different in terms of the costs associated with the production of these products. It's very different. However, again, if you were just interested in what would be the additional cost of producing, a certain quantity of cement, then this value here would allow you to calculate that. So then we wanted to come up with a means to kind of compare these different. So we have 4 industries. How do they compare in terms of their decarbonisation effects? Is one better than the other? Is it better to use biomethanation for a distillery or a pulp and paper mill? So we're just trying to compare them, really. So the first way that we wanted to do that was to look at what we've termed here decarbonisation intensity. So how we're defining that is how much carbon is avoided, how much carbon dioxide equivalent is avoided per megawatt hour of electricity, of renewable electricity that we use. So it sounds a little bit abstract, the way that we're presenting this data, but this data, the reason this data is useful is that this allows you to compare this method of decarbonisation with other uses of renewable electricity. We know we can make very large scale production of renewable electricity now. We have the technology, and we don't necessarily know what's the best way to use that renewable electricity in order to decarbonize our economy. Should you just put it into the electricity grid and allow it to be used in homes? Or should you divert it to hydrogen production for biomethanation in a steel, in a blast furnace? Well, this allows you to make some assessment of that, because what you can say is compare it with different uses of renewable energy. For example, if you just replace 1 megawatt hour of electricity, average electricity in our grid, with 1 megawatt hour of wind energy, wind produced electricity, you save about 0.25 is the kind of order of magnitude of that carbon saving that you make in our economy. So it's about 2.5 times more carbon effective as a use of renewable electricity than we've calculated it to be for biomethanation. So that's why we wanted to present the results in that way. The last one is our cost of decarbonisation. So this again is probably more obvious, immediately obvious why this is useful. So how much did it cost for us to decarbonise by 1 tonne of CO2 equivalent? So our unit there is pounds per tonne of carbon dioxide equivalent avoided. So we can calculate that for all of our processes, and they all come out in the kind of same order of magnitude. The kind of 800 pounds ish per tonne of CO2 equivalent avoided. The reason that that's useful is we can compare it with other options for decarbonisation. And I would say that it is significantly more expensive than other decarbonisation options that we have at the moment, which may be in the order of £50, £100 per tonne of carbon dioxide avoided. So this is something that is quite expensive as a means to decarbonise, but saying that, it is being used to decarbonise an industry or industries which are difficult, challenging to decarbonise. And so it's not necessarily the case that we should always go with the cheapest method of decarbonisation. Anyway, so those are the results we found. And for the last two graphs that I showed here, actually our different processes, it becomes less important, which of those four industries that we're targeting with this technology. The variability between them is much smaller than our estimates of uncertainty associated with these calculations. And so we could say they're all quite similar broadly from a kind of decarbonisation perspective. They do significantly decarbonise, but they are expensive, and there may be more efficient ways to decarbonise. So now on to the main conclusions of our work. What we found, well, biomethanation, in summary, can result in substantial decarbonisation of the four carbon-intensive industries that we assessed as part of this project. What's critical to that decarbonisation, the single most critical element, is where you get your electricity from, and that's predominantly to power the electrolyzer, which is the largest single consumer of electricity as part of this process, so the hydrogen production bit. And choosing the lowest possible carbon electricity, which at the moment in the UK is, well, it's close between offshore and onshore wind, but they are both very, very low carbon electricity sources. The third point here, the decarbonisation at the moment it is valid, but relies on this assumption that we have a natural gas grid, which is still predominantly fossil natural gas, or fossil methane. If this assumption in future is not the case, then the effects of decarbonisation using this method becomes less effective. Fourth point here, we can't get away from the fact that the cost estimates increase are very large, and this is especially the case for cement and paper, much less so for whiskey, with steel production being somewhere in between. And those additional costs are really dominated by the cost of the hydrogen itself. And that's even, I mean, there's various estimates of projections of hydrogen cost into the future. So we've used UK government predictions, and this is the prediction is it's still going to remain expensive to use that to produce hydrogen, even where you target curtailed electricity which otherwise would be curtailed, as in it's electricity that is you can purchase very cheaply, or even in some cases with a negative cost. So you are paid to use this electricity. Even with that, the cost of hydrogen is still predicted to remain high into the future. The last point here, which is kind of a thought a little bit outside our project because we haven't done any analysis on this, but it may be worth, in terms of kind of improving the economic viability of these options, to look at alternative high revenue products rather than methane, or obviously the effect of incentives, carbon credits, etc., which could skew the market to allow these products to be produced in using this kind of decarbonisation, whilst remaining economically competitive with other production facilities of the same product. Okay, so all that's left to say is a big thank you to our funders for funding this interesting piece of work. So our acknowledgement to EBNet and the Carbon Recycling Network for funding this work, and obviously their funding from BBSRC. The other acknowledgements should go to the collaborator or collaborators on this piece of work. So I've my main collaborator at the University of Sheffield was Dr. Davide Poggio, who we worked together to do this analysis. I should also note that one of my MSc students, so Namaka, also should be acknowledged as part of this work, as he did some of the initial calculations for the pulp and paper mill scenario. So thanks for the collaboration, and very grateful to the funders for funding this piece of work. And the last thank you is to say thank you to anyone that's listening to this. Hopefully you found it interesting. As I said previously, if you need to understand more about the methods we followed, the assumptions that were made, and to see the results, then please do download the report, so you can find the link below. Or if you need to cite that, we've also put a suggestion of how you would cite this piece of work if it is useful to you in any way. And if anyone wants to understand more about the calculations or have access to some of our calculations themselves, our data, then please do get in touch with either me or Davide, and we'd be happy to discuss that with you. The last slide that I'm going to show is just showing some of the data that we used to build our models, which just might be useful for some people to see a summary of that without having to dig into the report. But obviously there's a huge amount of input data needed to do these kind of calculations, and this is just a summary of some of the most important values. So that's it from me. Thanks for listening. See you later.